So last time we stopped that we wanted to discuss Maxwell equations as we have our fields in some medium, not just in empty, in the vacuum, okay? And as I said, then you have to worry because the presence of an electric and magnetic field itself modifies the atoms, whatever the medium is made of, producing, think of electrons or some atomic structures, producing some additional electric and magnetic fields, right? I mean, you modify the structure of this table, and there is a back reaction due to the atomic structure of the table itself. So you have to worry about when we wrote Maxwell equations and we wrote the charges and the currents, what those charges and currents are exactly, right? You really want to only worry about external charges that you put in the system or external currents, and not the many extra charges and currents that are due to the fact that you are stressing the medium through the presence of these fields. So one way well, this problem has been handled by, so for first you split your currents, right, in the Maxwell equation into what is the real current, that is a current that you put from outside, plus the contribution to the current that is induced, okay, as I said, by the presence of the fields themselves, okay? And the same you do with your charges, charge density, current density. You write an external part plus a induced one, okay? Is this clear? Is the problem clear, or you just want me to finish then go on to the next subject? You see the problem. You have an electric field, or as this field goes through this table, the atomic structure is changed, right? They move, for instance. For instance, you start having electrons going up and down, and themselves they then produce an electric and a magnetic field. And so you have you induce new currents and new charges by putting that table into an electric and magnetic field. So let's split what we put in the Maxwell equation with the density of current and density of charges in these two components, okay? So this is really the external one, and this is the induced one. And what is this part here then is usually written in this form, and you will see why in a second. So the induced current comes from two contributions. One is you understand, the polarization of your medium, and it goes, so the medium is polarized by the external fields, and the time variation of this polarization, induces a current. So you have a term that goes as a time variation of this. So this is called the polarization. Okay. And also you have, so this, if you wish, is the electric part. But you also have a magnetization of your medium, okay? And the curl of this magnetization is producing a current. Remember your Maxwell equations. By now, I hope you know them by heart. And so the curl of this, so this is the magnetization. Okay. So you have two new vectors, if you wish. One is the polarization of your medium. All your atoms are sort of deformed and aligned. This is the polarization. And also you have sort of magnetization, so through Maxwell equation, you know that it is the time variation of this that is inducing a current, and the curl of this producing a induced current. How about the the charge density. The charge density, again, if you have polarization of your medium, remember your Maxwell equation, then the divergence of this polarization is going to be linked through Gauss law to some charge density, and so it's put with a minus sign, and you have this term. Okay, so the polarization is here and there, and then you have a term that comes from. You don't have any magnetic contribution here, obviously, because that's the electric charge, so it does not. Okay. So it's kind of nice. It formalized this effect of inducing an electric current and charge densities through the effect of polarizing your medium and also magnetizing the medium. So if I take these two expressions, then, okay, you see I can replace my induced current density and charge densities by these two expressions. So instead of having this vector and scalar that I don't know what it is, I replace it with other two vectors that I don't know what they are. That is the polarization and the magnetization, and then I can plug these into my Maxwell equations. Remember, Maxwell equations, I guess, in these units are this rho epsilon naught. Let me just rewrite for you. And then I have the curls, right, minus d dt b, and then the one that is, so mu naught j plus this 1 over c square dE dt. So you see, if now I should replace this rho and this j by this, what I wrote here. So from the first one, I get, right, so I get dE, let's write it this for, so I have 1 over epsilon naught, then rho is really this plus this, okay, so I have rho external plus the induced charge density that, however, I want to write like the divergence of this polarization vector, okay? So this was for the first one. I don't... Now this one, it's okay because there is no charge. There is neither charge or current, so that this one stays the way it is. However, this other one here again, is the same, right? So these two are the two nice Maxwell equations because they don't have any external charge and currents. So these two, they stay the way they are. They stand correct. I have to rewrite the other one, right? The curl of B, right? And so this is mu naught. And then I replace this J that I have here with this. So I have my J, the external current densities. But now I want again to replace this induced one by this polarization and magnetization vectors. So I get these two extra pieces that I wrote there, dTp plus the curl of the magnetization. Okay, and then I still have dt. And now I sort of I do the usual massage. So because you see that the nice thing is that the polarization, of course, it was defined such a way that this comes naturally on the other side. So I can rewrite this pair of equations in a more suggestive way. That is, if I write divergence of, maybe I put right, I have maybe it's nicer to multiply everything by epsilon naught. So I think I wrote it like this, plus P equal to rho, right? You just, and the other one, I take the curl, but it's the curl of what? I have the curl of this B, right? Let's say write it this way. I take the mu naught, I take it on the other side. So I have the curl here, then I have a curl of M, so, but it comes with a plus. I take it on the other side, I get minus this magnetization. And this quantity is equal to this, the mu naught, I took it on the other side. So here again, I just have the external current density plus the terms that comes with the time derivatives of the electric field. So, okay. And at this point, as usual, so you see now the quantities appearing, you know, the same way that we had the electric field and the magnetic field in our original Maxwell equations in the vacuum. So these are in vacuum, or these are called microscopical. Okay, those are microscopic, as I said last time, microscopic Maxwell equations. This here, I can give a name to this quantity because you see that it is this quantity rather than just the electric field that appears everywhere. So I may as well give a name to this, and it's called D. Don't ask me why D, but yeah. Louder, I can. Polarization. Yeah, I forgot. You're absolutely right. I still have to collect. Otherwise, this trick wouldn't work. I have P plus epsilon dot E, right? I'll come because there is a, okay. Remember that 1 over c square, right, is 1 over c is 1 over the square root of epsilon naught mu naught. So you can, I'll come back to this in a second. So thank you. In fact, otherwise it won't work so well. So, and here I have the again, right? And this combination is called H. That is the this new magnetic field. So in other words, I can write exactly like so I can write a new set of Maxwell equations. Okay, these two we still say these two is just divergence. So I replace E by D, and in a way I have exactly the same equation, except that instead of having this microscopic charge density, I have the external charge density. So really the charges that I'm putting into the system, an electron or something, and I put this electron inside this table, okay? And this is the correct equation. And similarly, this one is replaced by this nice combination. So these are in a medium or micro Maxwell equations. So usually in the textbooks you will see these because these are the ones that are correct. But then you have to explain what these fields are. In fact, they even have a name. So let's dwell for just for a few seconds more on these questions. So this is the polarization, magnetization, and do I have a C square there? I'm not sure. I think, I mean, you don't have this C square, right? It's like this. Okay? So they, as I said, they even, so this D field is called the electric displacement. I mean, it's not important. I just give you these names because otherwise you go and read a book or something and then you don't know what they are talking about. We want it. This H is what is called the magnetic field. Yes? Well, I erase 1 over c squared, but in the process I also erase the plus.
Why they call it displacement?
That's, I don't know. I don't know. But you see, I sort of led you astray because I was calling B the magnetic field, but really what people call the magnetic field is this H. And so how do you call B? This is called the magnetic induction. And E is the electric field. So in this language, E is the electric field, H is the magnetic field. The other two are sort of electric displacement and magnetic induction. But I don't know, the way I studied when I was young, it was, I guess I was in the vacuum, so I always thought that, so I keep on calling that the magnetic field, but I guess you must know that this is. For us, it's not very, I'm not going, so it depends on what you do afterward. Of course, if you work in solid state physics or something that really has to do with matter, then you better remember this set of Maxwell equations. But if you then go on in doing high energy physics, then essentially you are in a vacuum, because when you go to very short distances, then the macroscopic structure of matter doesn't matter any longer, so really you think of these equations. But okay, the important thing is this, because sometimes this is very confusing. I mean, you have all this B, H unit. I think this explains what, I hope so, I hope to have explained for you, yes, this. Yeah, yes. Then I think you can replace. Yeah, okay, but then you can replace everything with the D and H. You do no, but I think you should keep this because that's what is really. I mean, the full set of Maxwell equations are with D, H, E, and B. I mean, it's not that you. Okay, it's a good point. It's not that. That would be really, that would be easy if I just tell you replace E with D and then okay. No, the real set is this one. But let me just, so this is all I wanted to say, but actually you see this is a sort of simplification. because well, now I erase it, but I assume that this was the end of the story, but actually the story is more complicated because now you want to know clearly what is the relationship between, so let's write it in component, for instance, the relationship between this electric displacement and the electric field. And the way I told you the story up to now is sort of a simplification because what I told you is that this is equal to epsilon 0. So the alpha component of the electric displacement will be just epsilon naught, the alpha component of the electric field. And the only difference is that you have to add a component of this polarization. But of course, this is a sort of a simplification because it's assuming that if you have some atomic structure, you apply an electric field, right? And then the only effect is this polarization. But really, you can have more complicated thing because you see, this is a sort of a linear response. But of course, the story is always more complicated. So you can think that you have higher order terms with some tensorial. For instance, this is what is this polarization? We will study this problem. This is what is called the electric dipole. That is the field generated by two charges of opposite sign very close to each other. This is the first effect, right? The atom starts out to be neutral, then you pull a little bit away the electrons from the proton. I mean, this is a cartoon. I mean, clearly it's more complicated. But at this point, if you are here, you start what was neutral is not neutral any longer because it's not the sphere screening completely the protons. So this is this term. But the story is more complicated because actually you have a distortion that is not just this pulling apart. So you have the next term that is called the quadrupole. That is a tensor, obviously, because life is like this. And it goes like a derivative of the quadrupole, I don't know, something like this. And so on and so forth. So this is usually the dipole term. This is the quadrupole term. Actually, very shortly, we will see that any charge distribution can be expanded, the potential of any charge distribution can be expanded in terms like this. You have the monopole, the dipole, the quadrupole, like a gravitational field. I don't remember, did we do that for the gravitational field? Maybe not. But this is, and so on and so forth, depending on the shape, right? Yes?
You don't have the tripole there.
No, there is no tripole. Why? I knew that you wanted to know why. It's a question of symmetry, if you want. You cannot make this. It depends on the field. Depends on the field. For instance, you can do the same. I mean, this is okay. It's still interesting. As I said, if you have a charge distribution, then you expand. Okay, and the expansion is you have a monopole, then you have the dipole. So what then is the quadrupole? There is no tripole or whatever you want to call it because there is no way geometrically to produce these terms. Also, you have a problem with the indices if you want to try that. But the same is for the gravitational field. For instance, the gravitational field of the sun. In our classical mechanics class, we already assumed that it was like if you have taken all the mass of the sun and put it in one point, right? That was the potential. And this term here is the monopole. But really, the sun is not a point. The sun is a sphere. Actually, it's not even quite a sphere, no, because it's a little bit squashed because it's turning around. So you may wonder, there is a dipole contribution. Well, there, for instance, is a case in which you don't have the dipole. And you see why you don't have a dipole for the gravitational field. Because to have a dipole, you need a positive and a negative charge. Because there is nothing to pull apart there. It's mass with the same sign. So the gravitational field has no dipole. So there is an example in which you have monopole, and then the first correction is a quadrupole. So it depends on the kind of field, what kind of terms you have there. Yeah. Well, it's the symmetry. of the body, the shape of the body for the gravitational field, and also the fact whether it is always attractive or it can have positive and negative charges. At the quantum level, this is carried on through the fact that, you see, if you have positive and negative charges, then the field is a spin 1 field, like the photon. So the graviton is always attractive because it's a spin 2 field. If you go on or if you think about it, well, you have to think really hard to get this. But the property of the quantum field are a reflection of this very basic property that we are studying here. So that's everything is connected. Yeah.
Can you consider sun has a graviton?
The graviton?
Yeah, sun.
The sun.
Yes, has a graviton.
No, the sun is not. No, the graviton is okay. This is outside our, but no, the graviton is what carries the interaction. Here, it's an electric field, right? This is the interaction, and is carried by the photons at the quantum level. Similarly, the gravitational interaction is carried by some field, the gravitational field, and that field at the quantum level is a spin 2 particle. The sun is the source. It's like the charge. The sun is the source, so it's like an electric charge. Then the electric charge produces a modification of space, time, actually. That is the interaction.
What is the graviton?
The graviton is, you have a field, the gravitational field. If you quantize that field, you have quanta. These quanta are the graviton. And what I said is that this quanta, right, is a particle. It has spin 2 because it's always attractive. Or maybe one should say vice versa. Because it's spin 2, it's always. This is the way Einstein discovered the theory. I mean, he first tried with a scalar, right? He say, okay, the interaction is carried by a scalar particle. It doesn't work. Then he ruled out the vector particles because he knew that if the carrier was a spin 1, it would have mass and anti-mass. He knew that, so he ended up with a spin 2. And unfortunately, spin 2 is a tensor field. So the theory of general relativity is the theory of a tensor field, not a vector field, like here. But that's... okay. No, but it's important to know, you have perspective. I think it's useful because otherwise you study only your thing, but they are all connected. At the end, you turn back and you see that they were all connected. So it's important to see also, to see this theory in the broader context. This is, after all, is just an example, particular example of a gauge theory, right? So you should see as a... So where were we? Okay, this question of the... So this is the electric displacement. So as I said, even here, this already was ugly enough, right? Because, but it's not the end of the story. So it's itself a simplification. And similarly, I must say that also this magnetic field, each component, these are components. You have 3 components, right? Because they are vector in space, in 3-dimensional space. You see, it's 1 over this B. Then you have this magnetization. But again, here then you have other terms. I'm not going to write them. So in general, what I did here was to stop here. So this is sort of the linear, if you want, approximation, or the lowest order approximation. But it could easily become much more complicated. And maybe the last thing you find in the book is that, in fact, if these corrections are small, meaning that you can keep essentially these first terms, as I said, then you see that the D field roughly can be written. You see, that means if these are small, this essentially the D is almost proportional to the field, to the E field. So you can introduce an epsilon without the knot E, right? Where this epsilon is this term here, something epsilon naught 1 plus K E. You see what I'm saying? If the polarization, assume that this correction is small, then you can think this polarization as essentially proportional itself to E. You apply the field, and the dipole that is induced itself is proportional to the field. It's not true, but it's an approximation. It's like the harmonical oscillator. And if this is true, also this is proportional to E, so I can write it as some new constant, E. And this new constant has this term, I guess here I should put the 1, plus some other constant that takes into account the dipole terms. And this in the books is called the dielectric constant. Maybe I can see it. There are too many something. There is no C, the electric. Okay? And it could be itself rather complicated. It could be a tensor, for instance. If it's not just a component, but when you apply an electric field, you get also components in other directions. You understand, right? If you apply perpendicularly, and then the only polarization is perpendicular, then it's just a constant. But if by applying the field you get also components in other direction, then this is it's a tensor. But okay, it is what it is, and it's called the dielectric constant in the medium, right? This is in the vacuum, and this part here is some other this quantify how proportional is this polarization with respect to the external field. And similarly for the magnetic field, I can do the same trick, right? I can write it as a new constant mu rather than mu naught, and again mu is equal to this mu naught 1 plus this I think it's called susceptibility. What? Something. Okay, we don't susceptibility. Anyway, you understand, is the constant, the proportionality of this term to the external B and E. No, it's called, I think, yes, and this is called the permeability. Very good. Again, this in principle could be a tensor if you get components in other directions. And I guess we can so I'm not going to talk about this any longer. I mean, we could spend a lot of time here. It depends on your approach on the subject. I mean, for us this is enough. Maybe just to suggest further reading, clearly this permeability is linked with this very important distinction that you know that all materials can be either diamagnetic or paramagnetic, and this depends on whether the ratio between this mu naught and mu is greater or less than 1. So these are diamagnetic, and these are paramagnetic. You know, everything is either diamagnetic or paramagnetic. Actually, there is also something that is called ferromagnetics. This is even more interesting, and for those of you who will go on into solid-state physics, that will become clearly very important. So what is a ferromagnetic material? Well, that's essentially a material for which this M, the magnetization, is there no matter, I mean, you don't have to apply an external be filled in order to induce this M is already there, because the atomic structure is such that is already magnetized in a way, right? For instance, the magnets, these things we started with, they are magnets, so they have a M that is intrinsic to the material, because some electric currents going around producing a constant ferromagnetic structure, and therefore this, even if you don't apply any external magnetic field, you do have a magnetic field because you have the non-vanishing M, okay? Those are very interesting materials, very important, and they are what they are. Okay? So that's all I wanted to say about this very confusing, at least for me, subject. And if there are no questions, I move on. So I hope at least this is the way you should understand but we will really stick to this set of Maxwell equations, but you must know that these are the macroscopic Maxwell equations, because somebody one day may ask you. Okay, so now we can, after this brief detour into notation and yeah. So what should we do that or not? Okay, let's leave this as an exercise that we solve together. So maybe Monday we don't have. So maybe on Wednesday we solve together these few problems. Okay, or you want to wait next Monday? It's up to you. You want to wait next Monday, meaning next? Okay, but then let's do this because we need it further. So we wrote the Maxwell equation. So let's stick for a second with this set with the E, B, and D, and H, so that we use, since we introduced them, we may as well. So we are really doing the theory in some medium. Okay, so that's the correct. And then you may. So I gave you the equations, and through these equations, you may wonder what happened when you have two different media. So 1 and 2. So you have your equations describing the physics of these fields everywhere, and up to now we didn't change anything in the. So this is a problem of boundary conditions, right? And so you may wonder how what are the boundary conditions for your fields when you cross a region of one kind or the other kind, and on this surface you have some distribution of charge and currents. Okay, is that clear? So I have my Maxwell equations. Up to now, I didn't put any boundary conditions. The space was everywhere the same, uniform. But you may cross regions in which space, some property changes, and in particular, you want to know what happened to your fields when they cross a surface on which there are charges and current. And I call K a two-dimensional current, so to speak, the current on a surface. And similarly, sigma is the rho on a surface, the usual, okay? So here you have E1, so this is the region EB1, and since we have introduced these fields, so these 4 fields completely describe the physics of your electromagnetic fields. As we discover, because this is not vacuum, you need not 2 fields but 4, or 2 fields plus those epsilon and mu tensors or constants depending. And up here, obviously, you have the same story with region 2. So how are these components, these fields, connected at the they must be continuous somehow, or with some discontinuity linked to the charges, and how you connect these components. So this is rather simple to do by means of the Maxwell equations. The Maxwell equation tells you exactly how these fields change as you go across this surface. And so they connect the field sub 1 with the field components sub 2. So let's do it first so all you have to do is to think of the Maxwell equations in an integral form, and then you see that if you take, so let's do first the set of Maxwell equations that they have to do with the divergence, or remember the divergence through the Gauss theorem is linked with the flux, right? So I want to study the flux through this surface, and to do this I take a very small cylinder, very small because I want to use the differential form of these equations. Well, I mean I want to use the integral form, but and you see I take it very small in such a way that I have essentially no contribution leaking through the sides of this cylinder, and all the flux goes through this face to the other one here, and therefore I introduce a normal vector, or better, a vector n that is normal to the surface of this tiny cylinder. And this is a cylinder, so this has a surface S and a volume V. You look sort of, I'm dealing with this integral, right? The S or dA. I wrote it dA, but yeah. You remember this is the flux of this vector through the surface S, okay? And this is linked by the first Maxwell equation to what? Do you remember? The integral of the charge in the volume V, okay? So this is d3x over the volume V, while the dA by area, A stands for area, so I guess, or if you want 2x is over the surface S. So this is first Gauss law, first of the Maxwell equation. So so I know this. Now I want to apply this to this situation, and to do that, I take for my volume a teeny tiny cylinder, okay? This is true for any shape, any chunk of space you want to take. And of course, here I want to take the one that helps me to get the result. So I want to study how the component of D changes going across this surface. Okay, so I squeeze this, I take a tiny cylinder, and you see if I do that, I get on this side, this is what? It's just the change, right? D projected along the normal direction, D2 minus D1. Times this surface S, I call it. Or let's call it dA. If I call this A, it's simpler like this. On the other hand, here I have this volume. I shrink these volumes down, so all is left is this charge density on the surface that I call sigma times the size of this surface. So I've done these two integrals by going into an infinitesimal small volume. Therefore, the integral becomes just whatever you wrote here, and then I apply what. Are you following or not? I'm doing the integral the old way, like Cavalieri did. I mean, you do the integral. How do you do the integral? You break up your integration in tiny, dx. Right, I'm doing so. One of these dx for me here, because this is not just the usual integral, is a surface integral. So my dx, I take it to be a small cylinder, and then I shrink it down here, and I make it sufficiently small that I can call dA is just delta A, okay? And then I just compute. And this integral tells me that the change from D2 to D1 projected along the normal directions is equal exactly to how much charge you have on the surface that you have included in your cylinder. Okay? So that's the first of the boundary conditions, right? Because I can, so this is equal to this, then I can eliminate the common factor, and I get the change in the electric displacement, D, is proportional to how much surface charge you have there. In other words, if you have zero charge on that surface, the D field goes continuously. And D2 is exactly equal to D1 because you have 0 here. Okay? How about the B field? What happened to the B field? You have a similar equation, right, for the B field, if you remember, right? That the flux of the B field around the closed surface, in that case, was not proportional to any charge because there is no magnetic charge. It was just equal to 0. So you can just replace in here the B and here the B, and you get that the B2 minus B1, right, is equal to 0. So in that case, no matter what, even if you have some current, some charges, still the B field, this magnetic induction goes continuously. So these two are the first two things you must know about boundary conditions, or if you want, about the D and B fields across a boundary. That the D field jumps by an amount proportional to how much charge is there. But this is very, I mean, it shouldn't come, it's not surprising at all. It's contained in the Maxwell equations. Rather, the magnetic induction goes across without any jump. It's just continuous. It's the same field going across. So that was about, remember, the components normal to the surface. How about the other components, the components tangential to the surface? Okay, you want a component tangential to the surface, so this I don't want to. So to study that, I do the other trick. Here I use the flux divergence, so integral over some. The other trick that we know only two tricks, either flux or circulation, right? So I guess I have to take a curl, and I take a curl again. I start with a curl like this along a circuit like this, and then I make this circuit very, very short here and just along the surface, okay? And now I use the other set of equations, okay? And I start now with H. So I go around this C circuit, right? I do an integral. Now it's not a surface integral, it's a circuitation, it's called a line integral along this closed loop of H along this loop, right? And I know what this is because I know Maxwell equations that we already wrote. This is equal to a surface integral around, so S. So I guess I should call this S prime because S was this, so this is S prime. Of J plus d dt n dA. Okay. Now, how about the well, here I have a flux, but I make this smaller, 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 okay? And if I assume that this is a finite quantity, by shrinking this circuit, so by shrinking the surface, this goes to 0, okay? Because this is a finite quantity. I mean, this does not go to 0 because I have this K current on the surface. But the other term is just some field all around that is proportionate to the surface. So it's constant, the surface shrinks, so this gives no contribution. So I'm only left with you see, the projection of the current along the surface, and this is what I call K. So here you must get this K, okay? So you see, I get from, so all is left here is this K, that is the current on this surface as I make this smaller and smaller. And on the other side, I have the two, see, I'm shrinking this, so I have the, on the upper side, I have the H2. And then when I come down, I have the H on the other side. So in other words, I have H2 minus H1, okay? I have well, it's like a curl. I have really the n cross this quantity. This must be equal to this current. Okay? So I see here that the change in the H component, you see, is a cross product. So the H, so this is orthogonal. This n is the same n, and then the vector there. So they are, these two are orthogonal. So this is the component orthogonal to both of these two. Similarly, if I do the same for the E field here, you remember that this is just for the E field, you only have the magnetic induction. You don't have a current there. It's the other Maxwell equation. Really, also the sign must change. But again, by the same argument, because I have a B field, I have a term that is finite, and then I start shrinking this surface, this gives 0 contribution. And therefore, in that case, so the n cross the change in electric field must vanish. So it's a sort of symmetric result. So these are the normal components. Okay. But these, you see, they must be the tangential component, because you see they are orthogonal to this goes like this, tangential. So by simply applying Maxwell equations through some cleverly chosen surface and loops, you deduce these important relations that are very useful. We will use them when we study some specific systems in the exercises. And essentially, you see that the normal components of these fields for the electric field changes proportionally to the surface charge. That's rather reasonable. The magnetic field has no surface charges, so it just stays the same. And the tangential are sort of the reciprocal, in which the tangential component of the H field, okay, these components, jumps by an amount proportional to how much current you have on that surface, while the electric field doesn't care about that current, and it just goes through in a continuous way, the tangential, while the normal one jumps by amount of the charges, okay? You are not very happy. Well, think about it. These are not new equations, you understand? These are, it's not that now we have 10 Maxwell equations. It's just the application of the Maxwell equations to this very specific way, so that each time you find this problem, you don't have to go back to Maxwell equations and think. It's rather easy to remember that these are the properties of these fields. And it's easy to remember because it's also reasonable, because you know that a charge produces an electric field, so this is what you have, some difference in the field inside from the one outside, if you wish, proportional to the amount. And the same, a current produces a magnetic field, and so you get an extra a modification of the H in going from one side to the other. Okay, so that said, yeah.
Can you make it a bit clearer?
I'm not sure that I can make it more clear.
Like, since D is finite, and then we make it one-ish, right?
We make them?
Yeah, d of t by dt.
I'm sorry, I'm not sure I understand. Why this does not contribute? You just because that's a finite term, right? So you shrink, you don't get anything. You have a finite term there.
I think everything is finite, right?
Yeah, but this one is a sort of, you see, this j goes down, 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 but there really you have, it's like you have a delta function, if you wish, in that integral. So you shrink it, but as you shrink, you get still this current at each point. At each point, you have this current. But the variation of the field is macroscopic. It's larger, and it's proportional to the volume in a way. So as you shrink the volume, it disappears.
Okay.
The current is locally there. So you shrink, you get that term. Okay. So we have just time to introduce so now, essentially, I have introduced the Maxwell equations. And so in a way, we have done everything, because that's what the electromagnetism is. It's just the study of the Maxwell equations. But of course, we cannot stop here, because otherwise. And so from now on, we start doing exercises in a way. So we start application of this Maxwell equation. So okay, is that clear? So we have the equations. Well, let's study these equations. Clearly, it will take some time, because as we did for Lagrange equations, to work your way through all the possibilities, and also consider how much more complicated are these equations compared to Lagrange equations, right? Lagrange equations were sort of scalar equations. They could become very complicated if you had many degrees of freedoms. And how many degrees of freedoms do we have here? These are fields in space. So we have an infinite number of degrees of freedom. That's the definition of a field. It's like having an infinite number of harmonical oscillators. So you understand that we are moving to the next step in complication. So don't be frustrated if sometimes you feel overwhelmed. But before that stage in which you feel overwhelmed, well, we all feel overwhelmed at that stage, let's do a very simple thing. That is, let's study the static situation. Let's freeze time and see what happened. And a wonderful thing happened because, remember Maxwell equations, right? But now, everywhere we had a partial derivative with respect to time, I take 0 because everything is frozen. And you see, the wonderful thing is, so now I switch back to E and B because that's what I like. So for the E field, you remember that this is whatever it is, but here I had this equal to minus dB dt, but now it's equal to 0. And again, here I had the curl of the B, right? It was this 1 over... okay, I decided to write it this way. So remember that E naught times mu naught square is equal to C square. So just to keep you this, sometimes I switch. Instead of writing mu, I write this. I don't know why, but it's a good exercise for you. And this was plus, right, dt dE. But now dt is frozen, so it's 0. And then I have my curl of B that is 0. So you see, very nice. So this is statics. Like in mechanics, we start from statics. And the nice thing is, see, they split. You can draw a line here. Before we had this electromagnetic theory, and I went on and on about how nice it was to have the electric field and the magnetic field unified, that by varying a magnetic field you get an electric field, and by varying an electric field you get a magnetic field. That's very nice, very powerful, but we are not ready yet for that. So let's switch off time, and we, again, in this world, the electric field and the magnetic field are completely separate. Because you see, these are two sets of equations, and I can study this set without having to worry about that. Or in other words, if I start out with 0 B fields, the B field will remain 0. And if I start out with 0 electric field, the B field will, the E field will remain 0. Or if I start out with no currents, then I only have an electric field. If I start out with no electric charges, then I only have a B field, right? So the two problems are completely separated, and I can start studying maybe this one first. This is called electrostatics. And this clearly magneto, where? Equal to 0. I'm sorry, right. Yeah, I'm a bit tired.
Where there is only B without E?
No, in general, no. I mean, in the Maxwell equations, here I have dB dt, right, minus. So I cannot, you know, I cannot solve these independently. To solve these, I have to know what B is. So then I have to solve these. And here too, I have a dE dt, right? So I cannot. So they are coupled. This is nice because it's telling me that these two fields are related. So in the real world, this is what it is. But in this ideal world of problem solving, right, of textbooks, you can assume that you switch off you study just statics. In the real world, there is no statics. You cannot freeze anything. Or you can approximate this by screening and all this stuff. But for the purpose of studying the subject and doing exercises, you can really split the problem. And so then you can study the electrostatics first, and then, or vice versa, but traditionally, electrostatics first, then magnetostatics. And that's what people in the old day did. In fact, a lot of 18th century, 19th century physics was about these equations, about electrostatics. Most of those special functions that you may or may not have studied, I don't remember if you did, like Bessel, Legendre, unfortunately you will see them again, they come from solving these equations. People wanted to solve these equations, and to do that, one of the techniques, as we will see briefly, is to use this orthogonal polynomial. Okay, so that's a very important problem in the history of physics, to study these equations. So so that's our next the next thing we want to study. But also maybe, so let me, so we will start on Wednesday. But I want to conclude by, there is something very nice that if you know, if you refresh your memory about vector calculus, you already know, and is the following. Let's forget, I mean, these are dynamical equations, you see, because they tell you if you have a certain charge, what the electric field is, right? For instance, from this one, we will start by rediscovering Coulomb force, obviously, because it's still there, hidden somewhere. This is a much cooler way of writing Coulomb force. I mean, it's sort of stupid, F equal, that's for kids. This is, is much sexier. But at the end of the day, this is still in general for a fixed charge is a Coulomb law. And here is the equivalent, it's called Ampere's law, that it tells you how the magnetic field is if you have a current. So it's there. But these two are kind of weird because you see they are not connected to any charge or current distributions. It's sort of the E field by itself must, so let's stop here and look at these two Maxwell equations. Okay, still statics. This is not true in the general setting because, well, this is always true, but this one is not true because you have that extra term. But let's forget about the extra term and let's look at these two fields just by these two equations. And so this is a curl-free field. E is a curl-free because if you take the curl. So by the way, when I write curl, you know what? The other day, as I was driving here, this doubt crossed my mind that you know what this is. This nabla is let's use Cartesian coordinates, right? It's a vector with this component, right? I mean, is that obvious to everybody? Yeah, no, I was just, I say, well, maybe. So if I take the divergence, that means I take dbx dx, right? Plus, okay. Very good. Otherwise, we. So this is a field that has vanishing curl. So that's a general field with vanishing curl. And this is a general field, if you want, if you wish, with zero divergence. So it's the divergence-less field. So I guess this is, so E is a vector field, right? This equation is telling me, with zero curl, okay? And a given divergence, because the divergence is given once you give me the electric charges. And then if you remember your vector calculus, you remember this very nice, that if you take a scalar field and you take the gradient of a scalar field, right, this is equal to 0. It's always, so the curl of a divergence of a scalar field always vanishes. But you can turn this around, and because this is always true, that means that the E field, because it's a vector field with 0 curl, is always equal to, well, there is a minus because of some convention. So you can always compute your electric field by another field that is called the scalar potential, like with the Lagrangian, right? Scalar, but it's not the same thing. So instead of studying the E field, that after all is a vector field with 3 components, you can always study the scalar potential that is a scalar field with only 1 component. And this is not, this in general is not possible for a generic vector field, but it's always possible because of this property if your vector field happens to have vanishing curl. And this is the case for the electric field static, in a static situation. So that's very helpful. And in fact, we will see that these equations can be turned into a basic equations, I mean, the divergence equation of the E field. Once you use this to replace E by phi, the phi field, sorry, and then this equation is gone. You have used it, okay? And then you are left with the one on the divergence that links the divergence of the E field to the charges, but there you replace the scalar potentials, and you will get an equation that is the equation we are going to study. It's called the Poisson equation. How about, so let me, so this was for the electric field. So this is very important. That's the reason why the electrostatics can be studied in a very systematic manner through this scalar potential. How about here, the B field is a vector field, okay, that's for sure. But instead of having vanishing curl, it has zero divergence, so 0. Okay, and reciprocal, it has a given curl. So this has a vanishing curl and a given divergence. This has a vanishing divergence, and a given curl. Now again, if you remember your this vector calculus thing, that if you have the divergence of a curl, this again is always 0, like there. And this means, right, because of that B can always be written as the curl of some vector A. And this is called the vector, see, the vector here was a scalar, vector potential. So as for the electrostatic equations, we essentially will be studying the scalar potentials. We can do the same for the magnetic field, the magnetostatic fields, and study instead of the B field the vector potential. But you see, the advantage is not as powerful as in the first case, because here you move from a vector field to a scalar potential, so you understand that you have some advantage in dealing with that. But here from a field you end up with another field. So what's the big gain? And in fact, in magnetostatics, essentially you stick to the B field in most situations. However, these two fields, the scalar potential and the vector potential, happens to be very important in many applications. And the first of which is that if you want to write the Lagrangian of a charged particle in an external electromagnetic field, that, remember, is essentially the Lorentz force that we studied the first day of this course. There, as I said, it's not very easy to introduce the Lagrangian by means of the electric and magnetic fields, but instead it's easy by using the scalar and vector potential. So in a way, from the point of view of the Lagrangian equations, the most fundamental fields are not E and B, but are phi and A, the scalar and vector potentials. Okay, so these potentials are interesting. We will need them to write the Lagrangian for the interaction of charged particles to the electromagnetic fields, and so we want to keep them. At the classical level, they are just auxiliary fields. There is no way to measure these fields. There is no a vector potential sort of, like a GPS or something that tells you how big. There is no such a thing as something that measures the scalar potential as well. So within classical electrodynamics, people thought of them as just auxiliary fields. But I don't know. I don't find this very. After all, as I said, also you don't measure E and B directly. You only measure forces, currents, charges, forces. So it's not clear to me if they have a different status, this vector scalar. Moreover, you may have studied this problem in your quantum mechanics class. At the quantum mechanical level, actually these fields have they can be measured in a way, because you do have physical effects due to the fact that you have, for instance, a vector potential. Meaning that in regions of space where you have zero magnetic field, but a non-vanishing vector potential, you have a phase shift in your wave function. Okay, this is called the Bohm-Aharonov effect, and I think maybe have you studied this? No? So maybe we'll briefly discuss it sometime, because it's important. Because it argues for the physical meaning of these vector potentials. Okay, and of course at the level of the quantum, the quantization of these fields, this quantization is essentially done on the scalar and vector potential, so they are even more important at that level. But at this level, for our purpose of solving simple exercises in electrostatic and magnetostatics, you can just think them as a trick, that because of these two nice properties, that a zero curve vector field can only be described by a scalar potential, and a divergence-less field can only be described by a vector potential. We move to these new quantities and study the equations for those. Okay, so next time we will do exactly that. We take these scalar potentials and plug into. So you need to know what the divergence, right? The divergence of a gradient is. And that is going to be the other Maxwell equations that I raised. So the divergence of a gradient is going to be proportional to the electric charge, and that will be our equations. And then we will spend, I guess, a week solving that equations that, as I said, is called Poisson equation. Okay, I'll stop here. Questions?